So we're going to move beyond rectangles and just adding stuff up. What we want to do is we want to be more sophisticated and understand that we are dealing with rectangles that have the width of, I don't know, a pinpoint, they're almost zero. And so when we add those up, we have the summation, et cetera, et cetera. We're kind of getting into the mind of Isaac Newton minutes and like kind of figured this out. So what we want to do though is we want to make sure that we understand negative area. So if you can read that, I'm not going to read it. If I actually had the integral of sine, say from 0 to 2 pi, do we recognize that the integral would actually be what? What's the value of the two areas put together? The answer is 0, because this guy is positive and that guy's negative. Those guys would effectively neutralize themselves. From 0 to 2 pi, the integral from 0 to pi of sine, and cosine for that matter, is actually 0, because they cancel each other out. All right, but we'd have to do, if we want the total area, actually how much it actually moved, we don't care which direction, then what we want to do then is we want to go from here to here, get that value, put it on something, and then we want to go from here to here, get that value, but make it positive, then add the two together. All right, so you have to think about, what is the function? Is it negative? Do I need this for my total area, or should I actually get the absolute value and then add it? All right, we're not going to go too much into that today, but just recognize that negative area is an issue going to have to be addressed. All right. Okay, so Leibniz introduced the notation of integral here. Isaac Newton's looks a little janky. The Greek letters of summation actually became Roman letters in the limit, so this is kind of like an S, okay, for sum. All right, and so the way that we read it is the definite integral from A to B of f(x) with respect to x. All right, so the definite integral from A to x with respect to x. All right, now with this, okay, now this is actually kind of an important concept, because it's saying that the x, right, the delta x, the width of your rectangle there is approximately 0. And what can happen is when we say with respect to x, we are talking about the x value, okay? We can actually do a with respect to y and change the orientation of our rectangles so that they're going this way, kind of perpendicular to the y-axis, and we can do a dy. Okay, so it's actually important, with which respect. You get into 3 dimensions, it could be with respect to z, the third, the height. So that is extremely important, right? And what can happen is you can have like a triple integral here for a 3-dimensional object with respect to x, with respect to y, with respect to z, right? Because you go do. So just keep that in mind, that it's actually very important that we put that dx. I'm going to be calling that a dummy variable for a while, because it's basically, it doesn't actually do anything for this beginning part of integration. All right. So what are the names here? I'm going to go in order here. This b is actually the upper limit. Okay. This lower limit. All right. This is actually, well, it's called the integral. Okay. That means this is actually the function itself. All right. But he has this name. He's called the integrand, which I will probably never say ever again. So just know that it is the integrand for the aspiring mathematicians. And this variable of integration. Okay, so the variable of integration just means where are we going? Are we coming from? Is the width x? Is the width y? Or is the width z? Okay, I mean, it all depends on what you're going to do. Okay, and the whole thing together is called a definite integral. Now, there are such things as indefinite intervals, and we'll talk about that later. I think it was Adam actually mentioned that you put this plus c when you take the antiderivative, and like we might in class at some point. So yeah, that indefinite means we don't know exactly what the area, but we know its family. Okay. Okay. So let's see. I'll finish this out here. The area. Okay, that is the displacement. Is by the x-axis. Comma, the function itself, and the vertical lines that are A and B. Vertical lines, so that would be x equals A and x equals B. Okay, so what that really is saying is this. I mean, you guys kind of already get the idea. Here's f of x, right? That's f of x, right? And if this was A and this is B, okay, this and this is this. Okay. Now notice that that's the boundary of the x. So these are the four boundaries: 1, 2, 3, and 4. All right, and that's actually going to give us that area. Okay. So let's go ahead and move to the next page here. I'm going to make these videos. Hopefully, that is about 5 minutes. Unfortunately, it doesn't tell me how many minutes this has been with Loom. Better. But you see, you guys have done this, so it's like it feels a little redundant here to have done 6, 4. So let's go ahead and function here, f of x. All right, he's a piecewise, a linear function here. Circle, half of a circle. Got some kind of here, another trapezoid there. So use this integration here, going from 0 to 7. Calculate the that. All right. So what I would like you to do is I'm going to go ahead, and I want you to calculate these areas on your own. Okay. And I'm actually going to go ahead and just put down. I'm not even going to discuss them. Okay. Except for you, that I'm sure is kind of an element of confusion. So why don't you go ahead and pause this? All right. And then go ahead and calculate them. And then I'm just going to put what's going on. All right. So pause the areas, and I'm going to go ahead and just so pause. Okay. So just for time, I think they split it. Series split at 5. I can't see where the colors are. They have like 8. I can't see visions on. All right, so let's just forget it. Formulas. The formula here is 0 to 7, so that's 7. That's so 7 plus 3. Cut that in half. Multiplied by the height, which is 4. That's 20. So it's a total of 20. This one is a total of, what do we got? You've got 3. 1, 2, 3, 4, 5, 6. Okay, so that's together, that's 9. Cut it in half. That is 4.5 multiplied by 3, which is going to be 13.5. So this whole thing is 13.5, and that's that. Okay. All right, so the answers to this. Looks like you're going to have to split some of these up. But I'll just kind of go forward. From 0 to 7, we saw that's 20. Okay. B13 actually is going to be a total of 6.5 and negative. So 5. Now from 0 to negative 6. Okay. From negative 6 to 0. From negative 6 to 0 is absolutely 2, but he's below the x-axis, so make sure that you made him negative. D is from 3 to 3. 3 to 3 is a sliver there, so that's actually 0. 0 to 7 is there's an issue, right? Because we should be going from 0 to 7, but here we are going from 7 to 0. Now, the interesting thing with that, and we're going to get into the rule later, that when you're going in one direction, right, you should be going from left to right, just the way that we read English, right? But if you're going in the wrong direction, what happens is that area then just negative, okay? In fact, there's going to be a principle or a rule that we're going to deal with in just a minute. All right, with F here, we're going from 10 to 4. So 10 to 4 is the wrong way. All right. So what I'm going to do, look these guys up. Let's use a different color here. Okay. I believe this area is, this was 8 and that was 12. Okay. And then from 10, I believe this was 15 over 2 or 7.5. Right? And that's 7.5, right? That's a total. You have 0.5, right? But you're going in the wrong direction. So then, therefore, it's negative 0.5, okay, or negative half. This wins, right? It's positive 8, negative, but because it's a positive 0.5, these limits of your upper and lower limits are reversed. They're going the wrong direction. And so negative. All right. So negative 8 all the way here, all here, add them all up, okay? And it looks like for G, we got 10.5, and then we are going to add a negative or subtract 9 pi over 2, whatever that is. All right, now, what is the slope actually at negative 6? This means, what is the slope at negative 6? You go to negative 6 here. All right, what is that? We have a line all of a sudden becoming a circle, and so that is a point. Do you know a point taking a negative there? Yes, it is undefined. Okay, now how about the double derivative of negative 6? All right, at positive 6, I mean. At positive 6, the double derivative here is, looks like it's negative 1, 2. So the double derivative, the derivative of negative 2 is actually 0. Now what's the average rate of change from 0 to 5? From 0 to these 2 points. Let me use a different color. Okay, the average rate of change, remember, is this slope from 0 to 5. We draw that, and we essentially do f of 5 minus f of 0 divided by f minus 0. You guys have done this 1,000 times. So what is f of 5? F of 5 is actually 4. 0 is actually 0. And 5 minus 0 is 5. So it looks like we get 4 over 5. That is the average rate of change from here to here. Okay? It was slower than that, but then for 3 minutes, it was 0. So that lowered the average. Okay? This was the speed or the average slope, but then this flat line essentially brought it down to here. So it is 4 over 5. All right. Now, if we go from 0 to 2, and then we add from 2 to 4, we add those two areas, area 1 plus area 2. Does it actually equal the total area between 0 to 4? Does it make sense? Yes. If we go from 0 to 2, and then from 2 to 4, if we added those together, it is the same as going from 0 to 4. So these areas are just additive, right? You can just say goes and just keep adding them on the x-axis. Over which values of x is different. Okay, so x is not differentiable. It's not differentiable at -6. It's not differentiable at 0. Then there's another point at 2, another sharp point at 5. There's another sharp point at 7, even though, yeah, definitely right there. There's one at 8. There's one at 11. Okay, I'm going to stop this and we'll continue in a second.